technical difficulties. All right, so sorry for the delay. Like before, I'm going to be sitting here during the presentation because I want to use a lot I want to change from one app to a different one. So let's recall what we did yesterday. We just went through a couple of Jupyter notebooks and saw how to use PyAlf to run a simulation. So that's something that we all did already. We opened something like the minimum ALF run, and we saw that okay, I can create an instance of the simulation, and I define what are going to be the parameters, or I can use the default values, and I just called the method for running it and called the method for analyzing, and I had some results, right? So that's all good, but it's time we see a bit under the hood. We touch a bit more in the real stuff, which is the ALF itself, not the wrapper around it, because there's still a lot we can only do directly with ALF, not if you use PyAlf. So first, a small tip. For most of the time, if you are a Git user, it's tempting to clone if you want to start from a repository. In the case of this repository here, let me try to make it bigger. I don't know how. In the case of the repository for tutorial and presentations, I suggest you don't do that. So if you want to have the folder, for instance, with the latest tutorial, the dev, just download this folder, because if you look at what is available, you have also presentations. So if you clone the repository, you're going to get like 7 gigabytes of recordings of previous years. So you probably do not want that. So that's the first thing. That's what you find. So if you download it, we're going to have the PDF that we also looked at it yesterday. So the first parts, I have it down here. I think it's better to look at it in a proper PDF viewer. So let's enter the dev, right? That's what we have here. So what we care about are notebooks. Yesterday, today we don't care about them. And of course, the tutorial itself. So I'm going to open it. We already went through the first part, the introductory part of this tutorial. So I'm just going to skip quickly. You can perhaps just to remind what I was mentioning a second ago, this part here. That's how we simulate, right? You say, okay, let's create this and say that this instance and say that simulation is with this specific model. Let's define like that, and so on and so forth. Okay, that's how it goes. And to have different notebooks, and then now I have this part where we want to look at the real code. Before that happens, I want to show a bit of ALF itself. You have already been offered many glimpses, especially today. Emily showed a lot of what you can expect to see in terms of the available Hamiltonians, for instance. She went into detail. We also have seen already how the parameter file looks, in part at least. But here's a part where for some people it's going to be easier actually to deal directly with ALF than with PyAlf, because here you have a structure that might be more familiar to many, which is to have a file that you can open with some editor and has the parameters. So here I am in some ALF directory installation. We have lots of things here. And one thing I want to go to is the start. In the run. And in the run, we have a file called parameters that we copied. It's always available. And what we have here, it's going to serve also as a reminder of what we have just seen with Emily. So I'm going to start from the bottom. In the bottom, I have the parameters for specific Hamiltonians. So that's been already explained pretty well. So I'm showing that mostly to say that don't get scared by the size of the of the file, because lots of those parameters are not going to be used in any given simulation because you're simulating one specific model. So the only one of those sets here, say the plain vanilla Hubbard or the TV, is going to be relevant for a specific simulation. If you look up here, we have those by now hopefully familiar sets of parameters about lattice, for instance, and a number of variables that we always need no matter what model you're using. They change according to the model, but you always need them, like number of flavors and the such. Then you also have variables which are also pretty general because they're not related to a specific Hamiltonian, but they are for the Monte Carlo method. They are relevant for the Monte Carlo method. So we have our already seen a number of sweeps and number of beans. Sorry. Among other things. So all the other possibilities that have been mentioned so far. Some analysis options like Rabinin and other specific ones. So that's how it looks. And then yesterday, at least, we had some people asking about, okay, so if I change the file I find in the results of the simulation from PyAlf, if I change the parameters there, then I can run it again with a different parameter. And that's not how it works because PyAlf creates that file to give you the information about the simulation that's being run. So here it would be like that. So if you open and edit this file here and run again and run simulation, then we're going to have a new simulation. So that's the parameter file. Another file that Faka and all others mentioned as being very important is after you make a simulation, you should always check the info file. So this is a case where a simulation has already been run. So we can also take a look at this file. And the info file is not big. A lot of it is stuff that we just saw in the parameters file. So it puts out the parameters that were used during the simulation. That's very important, right? Because we have a folder, a directory full of results. And if you don't, if you're not careful on how you name and how you place things, you might at some point, especially in the future, not know exactly measurements about what this was or which model to simulate and with which parameters. So it's really great to have this info file for that, so you can situate yourself, so you can see that, okay, so that was with 36 sides in a square lattice and so on and so forth with this Hopin parameter. And so this is good for bookkeeping. That's that first part here that tells you. So here it tells you the parameters for, say, repeating simulation if you needed to. This the same for the Monte Carlo aspect. And here the part that you should pay special attention to see if your simulation, to which degree you want to trust your simulation. So you're going to be looking especially at the mean precision that you get. So these are, of course, example values, so they're very nice. So I have 10 to minus 11, 10 to minus 12. Even the maximum value that during the simulation was achieved for the imprecision is extremely small. So this is all good. Acceptance, you don't want to run a lot without your flips being accepted. So it also should be reasonable. So it's good to take a look at those values to make sure that your simulation went okay. So much for those two files. They're very important. The rest of the files that you can see in this screen are results files. Another thing, it could be interesting to show, because we're going to be taking a look, a more closer look at it, are what you have in the core of the package. Let's just show a part of it. So here we have a number of yeah, that's not, I guess I want to go to Hamiltonians only. That's more like it. So this is essentially a summary of what we have just seen from Emily, with the difference that we have here also a template that can be very useful if you want to write your own Hamiltonian. There is a template available. It also tries to help with naming it according to our configuration or specifications, if you want. And important for us today, especially going to be in this tutorial, is going to be this specific Hamiltonian. It's called plain vanilla. It means that it's not written with the preoccupation of generality or trying to be elegant or anything like that. So it just tries to be as simple as possible to serve as a good starting point to understand how to change, how to write a Hamiltonian or change or modify an existing Hamiltonian, especially if you're not very confident with Fortran programming or if you don't program at all in Fortran. Okay. So we can go back to the tutorial. It's gonna be very similar to what you did for the introductory. So I'm gonna go through it, showing more or less what's there. Of course, not reading line per line, but that would be useless. But trying to highlight what I think are the key aspects and how I should go about it. The beginning should by now not be necessary. The beginning of this part here, which is about installing. Hopefully, it's not something that we still have to do. So you can go directly to the exercise 1. So this tutorial, this advanced tutorial, does not have really a presentation per se, only exercises. But they are not exercises like those at the ends of the notebooks for the introductory, which were just written there as tasks that you were supposed to use to train. We actually go step by step, telling you exactly what should be done. So the first exercise is very similar to something that someone wanted to do yesterday anyway, which is to have different hoppings in different directions in your lattice. So by default, you have hoppings, the same hopping amplitude in both. And the question would be, how do you change the files? So which files and how to change them so that you can have different values. So we're gonna modify the hopping. That's the first thing you do. As I said, we're gonna be basing, I hope that's big enough, but I can make it bigger. We're gonna be basing ourselves on this particular Hamiltonian, plain vanilla. And just to make it simple, we're gonna add a new variable because you could say, if you make it very elegantly, you'd probably want to have a parameter called hem_t x and hem_t y, one for each direction, but we want to minimize the number of changes I have to perform. So let's just leave hem_t as it is and use it for the x direction and define a new hem_t y. So what do I have to do here? Let's do the following. If you look at the folder for this tutorial, you see that besides the tutorial itself, the notebooks for the introductory version, some figures that you don't care about because they're just auxiliary for the rest, and the README, you have solutions. So we provided the files that implement exactly what is asked in the exercise. So let's take a look at those. So I'm going to go to solutions. The exercise 1 is here. And what we have here, so don't care too much for this latter part here. I'm going to mention them later on. What we have here is the original plain vanilla Hamiltonian and the one where the solution has been already implemented. Then you can take a look at. So again, the idea is not that you look at it and copy. That's why I'm going now step by step, so that you can try to then do it on your own afterwards. But now let's take a look at how they differ. So here's the regional. I'm going to compare it with the solution. I'm not sure that's big enough. Is it big enough? How do you judge it?
No,
Is it
make it a bit
bigger? Okay. So maybe here, maybe here, 9. Font. Didn't work. It does something else when I do that. If we're going to increase it, let's increase it for real. Okay, so here we are. This is the, so this, on the left we have the original, and on the right we have the modified Hamiltonian code. So this at the beginning is lots of comments, which allows us to have some automatically generated documentation, essentially describing the variables, not much more than that, and what it does. Submodules that are used here. Let's not care too much about that. So you are coming to the part that matters. So this is something that Emily also has described, and that's really it works actually pretty well. That before the break, we just saw the listing of the parts that have to be modified for you to change something in a Hamiltonian, and now we're going to look at a concrete case of these modifications. So this first modification is what you could consider as a side effect modification. So it's not the main modification you want to do. The main modification you want to do is to have a new a different value for the hopping in the direction, in the y direction. But what happens is that in Fortran you have to define the variable first. So that's what we're doing. We're gonna need it. So first I have to declare it. So I'm just saying that I'm gonna have some real variable with double precision. I'm calling it ham ty, and I'm giving it a default value of 1. That's all that's happening here. You say, how would I know that that's what I have to do? You just look above it. Immediately above it, you have this the declaration that existed already, which was for the variable related to the hopping, which in this case is in any direction. So we just create a new variable, which is identical to the first, except that it has a y added to it, to its name. Then you can take a look at the next change that has to be made. That takes part at the definition of the set. No, that's going to be afterwards, actually, right? No, it's here. It's also a collateral change. So it's not a change that I have. In this case, it's even a nice to have. It's not obligatory like the first. This is a nice to have change. I just said how it's important to look at the info file. This is the part of the code that writes this info file. So since you have a new variable, it's nice to be outputting the value of this new variable into this file. That's what I'm doing here. So write, again, you could just copy it from the above line and introduce it here. So that's all we're doing here. And even if you'd forget that, the program would run without problem. You'll just not be aware of which value of ty you had used. Here comes the real modification. And that's, I'd like to see more of it. Anyway, what we're doing here is the hopping itself. And what you see is that before, why do you have twice the epsilon y? Oh, right, because this is the part responsible. Both lines are responsible for the direction for the y direction, and what you had here before was that it was written in terms of ham t, just like for the x direction. And now you comment, or we commented out. You don't have to comment out. You can just edit it, and instead of use ham t, you use ham ty. That's the key change. That's the change that is proposed in the exercise, that now for this direction, you use a different value. And that's essentially it. What comes after, it's another nice to have. In case you want to use the projective mode, then you need to be able to specify a trial wave function, which also described in detail. And the same as before, you had some lines of code for the y direction, which used ham t, and now you want it to be differently, or at least in principle, be able to accept a different value. So you substitute the t by ty. And that's it. That's all there is to it. So again, The core is this change here, where you instead of using hemT, you use hemty for this part. A nice to have is the info file. A collateral, a need because of the programming language, though it's a good practice anyway to have the declarations, is that you declare the variable before you use it. If you forget to do that, anyway, you're gonna get a message, a compiling message, so you're gonna be reminded by the compiler. And the second nice to have, or not nice to have, you also must have it if you want to run the projective, but that's not part of the exercise at first. So that's it. That's it. That's it. That's what's to be done in the first exercise. We can go. So that's written. That's essentially what's in the PDF. Of course, in less detail, it's in part being described instead of shown because you don't want to have so much of the code repeated here, since you can just take a look at it yourself. And if you run that you can of course run it for different values of ty. In this case, we have a plot for 3 different values, 0, 1, and 2, while the hopping in the x direction remains equal to 1. And physically, it's interesting. I'm not going to discuss that because I already spent half an hour. I know we're started late. But I'll say essentially is how it decays much faster once you have a hopping value that's very different from 1. The description can be found in this paper, not so new. It's a ladder system. Okay, that's important. If you want to reproduce this picture, do read the tutorial. We are doing that for 14 times 2. So it's a ladder system. It's not a square system. And by the way, in case you would like to reproduce this plot, that's the role of those extra files here. So that file is our answer. The PDF is exactly the same plot you see here. And the PLT is a GNU plot script. In case you're familiar or want to use it, you can produce your own data and use the script to generate the plot. But that's really only a nice to have. It's probably better to use the time to play more with ALF and less with the GNU plot. But if you want, it's available there. And if you want to do that, let me go down here. If you want to do that, it's been written some time ago. I don't think it's stopped working, but there is a script, a very simple, probably not optimized script that changes the formatting of the output from the ALF to a formatting that fits better with GNU plot. Again, it's just nice to have. You can take a look whether it works at all. I didn't use it for a long time. I have not used it for a long time. In the exercise, it's also good to notice that we do provide a start folder, which means that you have parameters already here. So my comment about, don't forget to change the shape of the lattice, it's actually not something you have to worry about if you use the provided parameters file, because here it is, for instance, this, and you here, that's of course very important. You have to include in the parameters file your new variable. So let's see where it is. Here you have the part of the parameter file responsible for given the values we want to use for the plain vanilla Hubbard. And here you have our beautiful new variable, the hemty. Right? The program has to know what value you're given. Otherwise, it's going to complain or just use the default value. But then you can play around with it. This is something that you have for every exercise. We provide the start. We provide not only the solution, the modified Hamiltonian, but also the start, as well as the expected output. The part B of this exercise would be to perform the same modifications, having as a starting point not the plain vanilla, but the normal Hubbard. So the one that's not simplified. That's going to open up more possibilities. but it might be not so easy to do because it's longer and it might have different options you have to take into account. But then you can use, for instance, this part here, which is not available in the plain vanilla. So that's the first exercise. The second exercise is essentially implementing Hamiltonian, which is already implemented in the code. So you're not trying to do something new in this sense. Of course, it's an exercise, which is the TV model, right? Starting once again from the Hubbard plain vanilla and trying to just transform it from a normal Hubbard to a TV. So here there's something that I mentioned. We mentioned the possibility of creating a new namespace. Let's remember what a namespace is. A namespace is what you find, for instance, in the parameter file, right? You have those different namespaces for the different parts of the code, like only for the Monte Carlo or for the lattice and so on. So you have those different namespaces, and you have what I'm referring to here, the different namespace for the different Hamiltonians. And don't create a new namespace called the TV because it already exists, so it's going to be problematic. And my suggestion, differently from what is written here, oh, you could create a new one called T_V. Don't create a new one. Just modify the plain vanilla. It's just simpler and less prone to error. Okay, so just don't create a new here with all this convention of starting with the ampere and finishing with the slash. My suggestion would be to just come to this plain vanilla and make any necessary change here. So this part is a bit outdated in the sense that I would not write it again like that. Right, what do I have to change here that I'd like to mention before opening the file? This Emily has already explained, and from the point of view of the existing TV, and from the point of view of creating a new model, we're going to have a talk later on. So I'm not going to go through it. So let's take a look. What are the modifications? So again, I'm just gonna. So yes, I'm just going to open the original, comparing it with the modified one, and then I'm gonna see what sort of modifications have to be made. So this is not a real modification, sorry for it, it's a typo, so nothing's going on here, just an extra space. This is essentially a nice to have. We could perfectly well just keep calling him U and use it for the UI, but to make sure that we're not confusing variables, or to make sure that our changes being taken into account, we're just naming the interaction variable as V interaction, so hem V interaction. At any rate, just like before, we declared a new variable called the ty, or hem ty. Now we are introducing a new variable. So collateral changes. This is an important modification. Actually, if you look at what is written where is it? Here, one-dimensional TV model. So we're just gonna, we're doing that for the 1D case. So we also write a message, hey guys, if you're trying to use a second dimension different than one, no, don't go ahead. There's something wrong. You forgot. You said something wrong here. Okay, and also with the number of flavors. Okay. Here just what I said. We are not gonna be using, we're not gonna be outputting the hem u. We're gonna be outputting hem v int. But this is once again just a print command. It's nice to have, just so that your info file perfectly reflects the new Hamiltonian. So Again, a collateral change, we have to declare a new variable because we're going to be looping, and we want to have a new variable to loop it. It's just a counter. Again, related to the number of to the chain above, we change this one to true here. It's described in the tutorial. Bless you. And this is the part that introduces the Hamiltonian itself. So this is where, so it is taking place in the Ham V. So that's the heart of the modification. It's just implementing in form of code the Hamiltonian that we have here. In the way Emily described a little ago, right? We have a theorem. That's nice. That's nice to have. We're going to look a bit more at observables in the next exercise, but that's to say we have fewer observables because it's just one dimensional. So before we were allocating 5 spots of a vector of length 5. Now we allocate with 3, and we're not going to be worrying about these spin variables here. And so this is collateral changes. They must be done, but they're not. So it's important that you look at them, but conceptually they're not so interesting to us now. And here we have the same for the observables, because this is part of how it works. And here we have this is related to the 2 dimensions again. We have to calculate it a bit differently. And same here. This is a simpler change. This is really just a trivial renaming a variable. There's nothing going on here. Again, we had 2 of those. Now we only have 1. So this is a more complicated example because many things are going on at the same time. We are reducing the number of dimensions. We are changing the name of a variable, and we are doing the core of the exercise, which is introducing a new interaction. I want to have time for them, and then here you're gonna have for the time delayed observables, you're gonna have to reflect the same. It's the diff here is not showing well. The differences are less stark than they might seem. It's not like you changed everything those lines, but because I increased the font, the lines you have broken lines, and then it's hard to see where the differences stand. Okay, and the last exercise, because I know we do have a part B. So what's the part B? Yes, that's more advanced if you want to take a look into that. I want to use the last minutes to introduce, so we can discuss that later, but now I want to go to the exercise 3, because that's adding a new observable. And how it's done is something that's that Amy also explained today, so that's very convenient. It's really very convenient for me. And in this case, we're going to have to calculate what the background part to subtract from the main part, so the real measurement. And what this means is that in the code, we're going to see what it means in the code. Oh, no, sorry. It means much less. This should be very clear what's going on here. If you remember what the exercise is about adding a new observable. So if you have a vector of observables that was size 5, it's now going to have to be size 6. That's very clear. We have to say which is this new observable and give a name that's going to be used to create the file where the results are stored. It's a new type of observable that can be also time displaced. So for the tau, with this underscore tau, we also have to make it bigger, giving it a name as well. So this is all declaring and making a vector bigger. Another variable is just an integer to be able to store, and it's in this case not for looping, but for storing some value. And as you see here, we don't have to modify an existing part or comment out because we are really just adding a new observable. So here it comes. So in this case, if I could, in this case, we are really just, so you calculate following the procedure with the Vico theorem and writing it in the appropriate form for inputting it in ALF, and you just enter it. You just enter those variables the way we saw earlier today. And you have to do it twice because you have those two parts. You have those two parts that constitute your new observable. So we do it once here, another here. And then you repeat it for the time displaced. So so this is the kind of exercise where the actual hard part is coming up with those with this code. Yeah, so you have to calculate analytically what do you need, how can you write it in the correct form and translate it into code. That's the hard part. The other changes are relatively simple. So that's what I wanted to go through with you guys. We have about 15 minutes, if I'm not mistaken. Is that correct? No, we're 15 minutes late? No, we have 15 minutes. So we can use that for questions. It's probably not enough for you to start doing the notifications because I don't want to miss the next talk. But if you have questions, now is a good moment. We have enough time for them.
Yes, thank you. So, other questions? Maybe one comment. So once you have modified your hopping or your Hamiltonian, sorry, don't forget to compile the ALF before you run the simulation.
That's an important comment.
Yeah.
Yeah, so if you go to those details, don't forget to compile it. Don't forget to copy those parameter and seeds files from the start directory that comes with it, so that can run it with appropriate variables defined. Because if you look here, you're also going to have, of course, if you look here, you're also going to have, let's see if that's how it's done here. That's a good question. How was it done here? It might be that I just found a problem with our example. In the parameter file provide, no, it's a new observable. No, okay, sorry. I was looking for the vint, but that's something that we need for the exercise 2, actually. Okay, and there it is provided. Fine.
Yes. Yes, wait, let me give you the box. Gonna work, smart.
So if I rename a new Hamiltonian, I have to put it on the list also, right? Before compiling.
If you want to, yeah.
Yes. Okay.
That's also one of the reasons that we're always modifying the plain vanilla instead of just copying and creating a new one, so that you don't have to worry about this detail. But for production, well, I mean, if you want to really work with it, you should not call all your Hamiltonians plain vanilla. So if there are no further questions, no, because people might come only for the talk at some point, and then they don't expect. So if there are no further questions, I'm going to stop sharing. And we're going to be here in case of
Yes.
anyone needs something.
Yeah. So and we will continue in 10 minutes then with Annika's talk.